And welcome to today's lesson. In this tutorial, we will solve trig equations like we've been doing before, but this time we will find the values that are just on the interval between 0 and 2 pi. I guess we're in section 6.8, 6.7 and 6.8 deal with our trig equations. This time our direction for the day is solve for values that are just in the unit circle. Between 0 pi, we can include 0 pi, you see the bracket, and 2 pi. We're not going to include 2 pi because 0 pi is the same thing. So just unit circle values. I'd like to start off with this first one. We have 2 cosine of 3t minus 1 is equal to 0. Not too bad. I'm first going to get the cosine to be by itself, so let's add 1 and divide by 2. So the cosine of 3t is going to be equal to 1/2. And again, that feels nice. It's a unit circle value. So let's go to when the cosine is equal to 1/2 and see what we've got. The cosine goes to the right and the left. Positive 1/2 would force me to go to the right just a little bit. So we're talking about this angle pi over 3 and this angle 5 pi over 3. And since we're just dealing with those two, or excuse me, inside this interval, I don't want to call this negative pi over 3 because that's not where we need to be. So 3t could be equal to pi over 3, or 3t could be equal to 5 pi over 3. Now I'm not adding pi k's or anything like that like we did in the last time because we're just looking for unit circle values. Now we're actually not finished because we still have the 3 here. Let's multiply by 1/3, multiply by 1/3, multiply by, I'll do it on both of these, 1/3 and 1/3. So 1/3 and 3 go away. And it looks like our answers are going to be pi times 1 divided by 3 times 3. So pi over 9. It's one of our answers, and 5 pi over 9. And you'd think that we'd be finished, but we're actually not. There are more angles that we can be finding, and it's because we had to multiply by 1/3. Because we multiplied by 1/3, we made these unit circle angles tinier, which means that if we continued this pattern, not just pi over 3 and 5 pi over 3, but what if we did wrap around a few more times? Because if we divide by 3, we're going to get smaller values, and they still might be in this range, or this domain, I guess. So what we can do is say 3t could be equal to a bunch of things. We set it equal to pi over 3. We set it equal to 5 pi over 3. What I'm going to do is I'm going to start adding 6 pi over 3 because that's a version of 2 pi, and we can always add 2 pi to get to the same thing. So let's take this 1 pi over 3 and add 6 pi over 3, and now we're at 7 pi over 3. And we'll take that 5 pi over 3 angle and add 6 pi over 3 to that, and then we're at 11 pi over 3. Let's keep doing this. We'll take the 7 pi over 3 and add 6 more pi over 3 to now get 13 pi over 3. And let's see, we can take the 11 pi over 3, add 6 more, and now we're at 17 pi over 3. Now clearly all of these angles are bigger than 2 pi because 7/3, 11/3, 13/3, 17/3, these are all numbers that are bigger than 2. So I know that these angles are no good, but if we're going to cut them in thirds, if we're going to divide by 3 or multiply by 1/3, we will possibly get angles that are less than 2 pi. So I went from 7 pi over 3 to 13 pi over 3, add 6 more, and I'm at 19 pi over 3. I could do this all day. I know. I'm going to stop right here and let's see what happens. If I multiply by 1/3 on all of these equations, and multiply by 1/3 here, of course, since it's an equation, we have to do the same thing on both sides. Let's see what happens. 7 pi over 9, well, that is a number that's less than, is an angle that's less than 2 pi. Heck, it's less than 1 pi. 11 pi over 9, Yep, that's going to be less than 2 pi. In fact, I know that it's going to continue to be less than 2 pi as long as the numerator does not exceed 18 pi. Once we get to 18 pi over 9, then we are at exactly 2 pi. So here's 13 pi over 9. That's still good. Here's 17 pi over 9. Oop, we're getting close. This one would give us 19 pi over 9. This one we have a problem with. This one is when we start to get too big. We get out of the bubble that we're looking for. We just want between 0 and 2 pi. 19 pi over 9 is just a little bit bigger than 2 pi. But there are 4 other answers. So we have the original 2 that we found, but then if we continue to find our bigger and bigger coterminal angles and then do the same math, we get 4 more answers that are in our range, or our domain, I guess, of 0 to 2 pi. So another thing that you could think about, if you have a multiple angle, this is 3 times the angle t, this is sort of like that you're going to have 3 times as many answers as you thought that you would. When you go to the original unit circle, you have 2 original answers, but because it's 3 times as much, there should be 6 answers, and that's why we have a total of 6 answers for this one. So that's kind of fun. Let's look at another one. Another multiple angle here. It's not really a multiple angle. I guess this is more of a half angle because it's 1/2 of x. It's a tangent, and I'm going to get tangent to be all by itself. Let's do that first. We'll do the tangent of x divided by 2. Subtract 3, divide by 3, and we'll have that equal to -1. Feels good since that's a unit circle value. I have to remember where the tangent is equal to -1. Well, I remember that that's the 1 in the middle. The tangent is going to be equal to 1 in the middle of all the quadrants. It's going to be equal to -1 in the second and fourth quadrants. So those are the 2 angles that I'm talking about. I know that this x over 2, the angle, right now it's just x over 2, I'll deal with the 2 in a minute, could be equal to 3 pi over 4, or the x over 2 could be equal to 7 pi over 4. Those are the 2 angles from my unit circle. Now what am I about to do? I'm going to get rid of this 2 by multiplying by 2 this time. I'll multiply by 2 on this one as well. And let's see what we've got. X is going to be all by itself. And we have, well, actually 2/4, that reduces to 1/2. So it looks like it's going to be 3 pi over 2. Or you could just multiply and get 6 pi over 4, but that reduces to 3 pi over 2. And let's see what happens here. I get 14 pi over 4, which is 7 pi over 2. Either way you do that, 7 pi over 2. I think we have a problem with that one though, don't we? If our angles have to be between 0 and 2 pi, this is too big. So the only answer that works is this one. And again, we thought we were going to have 2 answers because the unit circle has 2 locations where the tangent is equal to -1, but because there's a 1/2 in front of the angle, only half of the answers will actually be the answers. So of these 2, it's just one of them, 1/2. Moving on to example C, we have the cosine of x plus 1 is equal to the sine of x. Now in the previous tutorial we dealt with equations that had 2 different functions on our variable. Obviously sines and cosines are not the same function, but in that tutorial we had chances to factor or to substitute or to do something to change cosines into sines or sines into cosines. There's no way that we have to change this cosine into a sine and the sine into a cosine. In fact, there's really not much we can do right now. What are we going to do? I wish we had some sort of squared stuff, that we could use a Pythagorean identity. Well, how can we get squared things? How about we just square? Now, squaring means that you take the entire side of the equation and square. You don't square each piece. That doesn't make any sense. You have to take the entire side, put a parenthesis around it, and square it. And this is absolutely a fine step to do in an equation, as long as you check. Just like taking the square root, you have to remember the plus or minus symbol. When you square, you have to check. And here's the reason. I can come off and explain that. If we have a simple equation like this, x equals 3, obviously the solution is 3, and then we square both sides, we would have x squared is equal to 9. And when we square, sometimes we come up with what's called an extraneous answer. Now there are two solutions to this equation, and we say that x is going to be equal to plus or minus 3, because that's what happens when we take the square roots. But obviously only one of these solves the original equation, and we have to check and make sure that the negative 3 is not there. So whenever we square, sometimes we can come up with extraneous answers that do not check in the original. So you please must check at the end of this problem. Maybe just make a little asterisk or a little note. Okay, so let's square. So this is a cosine plus 1 times another cosine plus 1. There's no way of getting around the fact that we have to FOIL. And this is just a sine squared. I can do that one pretty fast. Let's go ahead and FOIL this one. First outer, inner, last. We get cosine times cosine is cosine squared. The outer terms are one cosine. The inner terms are another cosine. So there are two cosines in the middle. And the last terms are a 1. Okay. Now we still have the same dilemma. We still have two different functions, but at least now what we can do is we can replace one of them to rewrite it in terms of the other one. Sine squared, we could call that 1 minus cosine squared. And that's what I'm going to do. I'm going to leave these where they are, and I'm going to replace the sine squared with 1 minus cosine squared. And now I have an equation that only involves cosines. Now it does look like it's going to be a quadratic form, so I'm going to set it equal to 0 and try to factor. Let's add our cosine squared term to this side. I'll put it underneath its like term. And let's also subtract 1. So nothing will be over here. There's my 0. I have 2 cosine squareds plus my 2 cosine. And actually 1 minus 1 cancels out, so that term goes away. That's kind of nice. Now I'm left with a binomial. Binomials have special patterns to factor them. In fact, I see the GCF right now. I don't really need the 2. I could just divide everything by 2 right now and just get rid of the 2. Sure, that's fine. So now I have cosine squared plus cosine is equal to 0. And now I can factor out that GCF. I see that they both share a cosine, so if I pull a cosine out, I'm left with cosine plus 1. Those are my two factors, finally. Setting each factor equal to 0, I've got that the cosine could be equal to 0, and I've got that the cosine could be equal to 1. Excuse me, negative 1. I'm going to subtract the 1. Negative 1. Now, when is this going to happen? Well, let's go off here and draw our unit circle. And let's see what we've got here. The cosine is equal to 0. That means I'm not traveling left or right. And the two angles that would make that happen are here, the top and the bottom of the unit circle, 0, 1, and 0, negative 1. So I'm going to say my answers here. I've got pi over 2 and 3 pi over 2. And there's a third one. Let's see, the cosine is negative 1. That's when we go all the way out to here, and that is at pi. So apparently I have 3 answers. But I remember my original note that I needed to do. I need to check. And I need to check each one of these. And I need to check them in the original function. Or excuse me, the original equation. Let's start with pi over 2. Take the pi over 2. I want to know what the cosine of pi over 2 is. The cosine of pi over 2 is 0. And 0 plus 1 makes this side of the equation 1. Sine of pi over 2. Sine of pi over 2 is equal to 1. So therefore 1 equals 1, and we have it. Let's check 3 pi over 2. Plugging a 3 pi over 2 into the original, cosine of 3 pi over 2 again is 0, and 0 plus 1 makes this side of the equation 1. Sine of 3 pi over 2, Sine of 3 pi over 2 is down 1. That's negative 1. 1 does not equal negative 1, so bye-bye. That is not a correct answer. So 1 worked, 1 didn't. I wonder what happens with the third one. Let's do pi. Cosine of pi is negative 1. Negative 1 plus 1 makes 0. So this side of the equation is 0. And the sine of pi is 0. That works. 0 equals 0. So that's one of the solutions. So we only have 2 solutions. One of them became an extraneous one, and it's because we squared. I have 2 more examples. Let's look at example D. So example D, it looks like we have the same sort of dilemma. We have 2 different functions on our variable. We have a secant and we have a tangent. At least we have something squared here, so it looks like we can use probably one of our Pythagoreans. Now we do need to remember what secant squared is equal to, and that is equal to tangent squared plus 1. Or some people memorize it as 1 plus tangent squared. Doesn't really matter. And that first step gives us an equation that only deals with tangent. So that's very nice. I like that. And we still have a tangent squared, so most likely we're going to be factoring. So let's get everything equal to 0. I'm going to subtract the 4, put it underneath its like term, and I'm going to put the terms in the order. I'll get the tangent squared term first, then I'll put my negative 2 tangent, then 1 minus 4 is negative 3, all set equal to 0 so that I can factor. Okay, let's factor this one. There's only one option for the front, tangent times tangent. I like that. There's only one option for the back, 1 times 3. Okay, so this shouldn't be too bad. Tangent and tangent must be in the front of the parentheses. Still set equal to 0. The 1 and 3 have to be in the back, and I need a negative 2 tangent, and I know that my signs have to alternate. So I'm going to put a negative with the 3 and a positive with the 1. Just do at least a quick mental check. I see 1 at tangent in the middle, and I see negative 3 tangent on the outside. Negative 3 plus 1 makes negative 2, so I know that I'm correct. Now let's set each factor equal to 0, so I can get my little equations. Subtract 1, and I've got tangent is equal to negative 1. Feels good. This one I get the tangent is equal to 3. We'll deal with that one in a minute. Let's talk about our unit circle. When does the tangent equal to negative 1? I believe we saw this one before. Negative 1 is going to be the one in the middle, and it's in quadrants 2 and 4 where it's going to be negative. So x equals 3 pi over 4, that's one of them. And the other one is 7 pi over 4. Now, there should not be any reason for us to check these. Of course, you can check them if you want to, but we don't need to check because we did not square anywhere along the way. So as long as our math is correct, these must be the correct answers. Now let's move on to the second one. Tangent's equal to 3. That is not one of our unit circle values. Don't confuse that with square root of 3. Square root of 3 is one of our unit circle values, and that happens at pi over 3, or at the pi over 3's. This is just straight 3. This is not one of our special angles or values, and but it does not mean that we cannot do this problem. It just means that we're going to need some sort of technology. We're going to use our calculator. We're going to have to use our calculator here, and we're going to do an inverse tangent. So let's pull up our calculator, and let's make sure that we're in the correct mode. All of our angles so far have been in radians, and I'd like to continue for them to be in radians. So I see that I'm in radian mode. Check your calculator, make sure you're in the correct mode. Okay, we are doing, let me pull this over a little bit more. If the tangent of x is equal to 3, then that means that x is going to be the inverse tangent of 3. And let's see what that's going to be equal to. We'll just have our calculator do it. Inverse tangent of 3, and I know I'm in radian mode, and I get 1.249. Now the pi is already multiplied in here, so it's just 1.249. Okay. And I'm going to put approximate, because it is irrational. 1.249. Now, I don't know exactly where that is, but I'm sure that it's somewhere around here on our unit circle. The question is, how are we going to find the other one? Because if the tangent equals 1.249 here, there is another, or excuse me, if the tangent equals 3 at this angle, this 1.249, there is another angle on the unit circle where it will also equal that. And I do know if the tangent is positive 3 here, then exactly 180 degrees away, it should be another angle where the tangent is equal to 3. How am I going to find this other angle? Well, I sort of just gave it away, didn't I? What's the distance between these two in terms of radians? They're exactly pi units away. If I add pi to this angle, I will have this other angle. The calculator is not going to help us in terms of just inverse tangent. If I type in inverse tangent of 3, I will always get this angle. I'm not going to get the other angle, because the inverse tangent only exists, at least in the calculator's programming, on this side of the unit circle. But we know that there's another angle. All we have to do is add pi to it. So I'm going to take this angle that I just found, 1.249, and I'm going to add pi. Pi is right here above the little caret. 4.391. 4.391. So that's why I'm showing you this problem. So far we've been lucky and we've always been dealing with a unit circle value, so I can just use the picture of my unit circle. Sometimes though you might get a number that is not in the unit circle, so therefore we would use some sort of technology to find the angle and understand that we can always get to another angle using our knowledge of the unit circle, that all the positive tangent values in quadrant 1 reappear in quadrant 3 exactly pi units away. So thanks for watching that. And then we have our last equation. It looks like such a simple equation, and it actually is in terms of how we're going to solve it. This is the first time we've seen the variable, and it's not actually one of the angles. We've seen the variable always as like the sine of an angle or the cosine of an angle. This time it's just this number. You can try a bunch of algebraic moves. You can try squaring both sides, or I don't know, setting it equal to 0 and trying to factor. Frankly, I don't even know how to solve this using an algebraic technique. I'm going to use my calculator. What I'm going to do is I'm going to set it equal to 0. I'm going to bring the 2 sine x, I'm going to make it x minus 2 sine x. I'm going to set it equal to 0, and I'm going to use my graph. I'm going to graph this on the calculator. This is sort of a cheating way of how to solve any equation. If you're having trouble solving any equation, just set it equal to 0, of course, and plug it into y equals, and just look at the graph. If it has any real solutions, you're going to see them as x-intercepts. So I'm just going to plug this equation, solve it, set it equal to 0, and then plug it into the calculator, and see where it crosses the x-axis. So what do I have here? I have x, I know I'm still in radian mode, x minus 2 sine x, close my parentheses. That's what the equation is, and I want to know when this equals to 0, or rather, where it crosses the x-axis. And it looks like, yep, there we go. It crosses the x-axis 3 times. I see it crosses here, and then here, which looks like 0, and then right here. And if you notice, it's a sine curve. It's a sine curve going up a diagonal line. It's actually going up the line y equals x. Kind of an interesting graph there. I just need to have the calculator calculate the 3 solutions. I'm going to go to the table and confirm that it looks like the middle solution is 0, 0. Yeah, it is. So when x equals 0, y equals 0. So I'm not going to use the calculator to calculate that. I know that that one is true. So I've got x equals, I can use an equal sign, 0. You could say 0 pi if you want to. And x is, I'm sure that the other ones are going to be approximate values. And let's ask the calculator to calculate them. I'm going to go to the calculate menu right here. So second, calculate. I'm looking for what's called the 0, number 2. And there's my cursor. I'll just find this positive one first. And it looks like it's in between. I know that it's in between 1 and 3. So for my left bound, I'm going to choose a 1 and press enter. And then for my right bound, I'm going to pick 3 and enter. What the calculator has just done, at least in this operating system, it's shown me that I've chosen 2 numbers and my 0 is supposedly in between them. And I can verify that that's true visually. I'm going to press enter for my guess, and it's going to give me 1.895. So approximately 1.895. And then there is another one, and I imagine that it's going to be exactly symmetric with that other one, so therefore it's probably negative. I'm going to do the steps again just to verify. Second, calculate, it's number 2, my 0. And this time I'm going to use a left bound of -3 and a right bound of -1. So -3, enter, and -1, enter. Again, I'm telling my calculator a window of where I think my 0 is. And I'll press enter. And yep, I was correct. -1.895. -1.895. So those apparently are our 3 solutions. But hopefully you've already caught our mistake. Only 2 of these are actually going to be our solutions. I'm just going to circle the ones that we're actually going to be using. Why am I not using the third one? Because it's negative. This number is not in our interval that we started with from 0 to 2 pi. So we'd never needed to calculate that anyway. Okay, so this one is very tough to solve algebraically. Like I said, I don't even know how to do it. I cheat and I use my calculator and I look at the graph and I see the x-intercepts. It doesn't give me an exact answer, no, but it gives me an approximate. Thanks for watching this tutorial. We've got a lot of review to do on this topic, and I'll see you in class. Thank you very much. Bye-bye.